So, welcome to my dear friends and learners. So, today we will continue about the delayed neutron, and we will learn one more important application of a delayed neutron. So, in the last lecture, we have established the instantaneous uh, equation for the neutron growth in a fission reactor when the effect of delayed neutrons are considered. And we saw that there are two roots, omega 1 and omega 2, and this lambda. So this is omega 1 and this is omega 2. So this lambda is the average uh, decay constant for combining all the delayed neutron precursors group, and it says the value is typically small. So if you see the roots omega 1 and omega 2, the amplitude of omega 1 might be much more smaller than the omega 2. So then we have neglected this term, okay, and only we kept the omega 2 term because that will contribute significantly um, during the neutron population. And here you can see this beta minus rho one term is there in the coefficient as well as in the omega 2 also. So for here it is very clear that uh, because this is a negative quantity, so this rho definitely should be uh, because uh, this term should be negative actually, then only negative into negative it will be positive. So this r- rho should be actually here, if you see, just when this uh, this this beta and rho, this will become equal, just tends to equal, then this will be these things, it will be once it is nearing to beta, this rho reactivity, so that time uh, this again the equation, it will be converted to this equation will be converted to this, and that time only using the prom neutron uh, the fission reaction will be achieved, and that condition is called prompt critical. So all these things we uh, discussed in the previous lecture, and also the application means the importance of delayed neutron, how delayed neutron contributing for a controllable neutron uh, growth in the in the reactor chamber, that uh, the transient, the occurrence of transient is nullified. Now the question is coming, how the neutron, this delayed neutron, it will be detected. So we know the neutrons are neutral particle in the nucleus. Neutrons are neutral, and therefore when it is passing through any matter, it cannot ionize it. So they can't be normally detected straightforward. It cannot be detected by the nuclear detector, which used the ionization chambers. Okay. So for the neutron detector, some indirect process is to be adopted, which by absorbing the neutron, it will produce some charged particle, and that charged particle will count to quantify the delayed neutron. Normally, fission chamber may be used. There will be a chamber. The inner lining of the chamber should be a chemical. This we have a deposition of enriched fissile material, and once the neutron will absorb there, this will create some uh, ionization. The fission will occur, and this will mm, the fission fragment will go for beta decay and all, and that will in turn uh, uh, that can be counted to measure the delayed neutron. This QR code, you can scan the QR code here. The fundamentals of nuclear detectors are explained, different types of these things. So you can see that, you can refer that. Another important thing is in nuclear fission, that is the reaction cross section. In nuclear physics, the reaction cross section is the basically is the measure of the probability that the nuclear reaction will occur when a particle like neutron interacts with a target fissile nucleus. Okay. In this aspect, so for delayed neutron detection, you should remember, because it is a slow neutron. Okay, the velocity is less, because if you remember, this will in contrast with the prompt neutron, this delayed neutron, it will release uh, in much more after much more delay, uh, after the fission occurred. It may ranges from millisecond to minute also. Okay, that will release from the um, uh, delayed neutron precursors, or the fission fragments. So this in this aspect, 1 over v law, I think all you are familiar that here this law describe that how the reaction cross section depends on the neutron velocity or energy, especially for thermalized neutrons. Okay, so if the as the name suggests, so the cross section is inversely proportional to the neutron velocity. Okay, as the neutron velocity decreases, so eventually it spend more time near to the nucleus. Basically, this increases the probability of neutron atom fissile atom interaction. Okay, so hence slower neutron will basically provide the higher cross section. Okay, so normally for slower uh, uh, neutron detection, the boron detector will be used. Okay. And the neutrons are redirected to the chamber, which is filled with boron trifluoride gas. Okay, and this is the reaction happened once the neutron is absorbed by the boron, and it will release alpha particle. So basically this is a charged particle, and by detecting that alpha particle, you can indirectly count the delayed neutron. Okay, Another major, another major one a very important application of delayed neutron is to mainly in the fast reactor is to locate the failed fuel. So if you see the a fuel subassembly, so inside the fuel subassembly there will be some fuel pins, and through that uh, the the coolant will flow actually to the fuel pin, and based on the mass flow, the heat transportation will take place. Okay, so if you want to know more about the velocity distribution inside a fuel subassembly, so one detailed video is there. By scanning this QR code, you can refer this particular QR code link, so that you can understand in details. There is a mathematical derivation of the velocity distribution inside the fuel subassembly. So normally the fuel is provided with a leak tight metal cladding for containment of the fission product, because after that, after complete burn up, that should not be come out, and it should not mix with the coolant, because that will, if it is coming out from the subassembly or the cladding, and then that fission product may block the coolant flow, okay, in the subassembly. So normally the failed fuel means we will consider those fuel whose some of the pins are the clad of the some of the pins are ruptured. Okay, so how to identify that? So to identify that, one simple rotating driving mechanism is used. Using that particular structure mechanism, the coolant which is coming out from the subassembly, it is taken, and just we have to check whether the delayed neutrons are present in that particular uh, sodium flow which is issued from that particular subassembly. So if normally the fission fragment which is enriched with neutron, so those will basically the fission product who are those are delayed neutron precursors. If that is due to clad failure, if it is mixing with the coolant, and that if you take it somehow, you can, if you can take it and check whether the delayed neutron is present there or not. From that you can easily understand that the clad has been ruptured. Okay, so this is the basic techniques. So here you see, this is the basic structure of that. It will be normally, typically in case of fast spectrum reactor, there is three numbers of this failed fuel location module will be housed in the control plug. Okay, and this is a sodium sampling sleeve. Some it is concentric over each thermocouple passage, which is top of that where the thermocouple is there. So there, it is the tube is there positioned of particular subassembly, and the other end of that sampling tubes are connected to the base plate. These are this red color, these are the base plate. Okay, uh, then the sodium which is coming out from the particular subassembly is passed through these sampling sleeves, and reaches here. This is called a selector valve, and then it is permitted to that whatever the sodium is coming out, so that it is connected, this you see, this tube is connected to a DC conduction pump. It is simply Fleming left hand rule, and that it will be pumping to a storage, or you can tell it's a sodium capacity here, and then from there it is again through a flow meter, it is again uh, returned back to the hot pool. Okay, and once this sodium is taken and from this area, and this is the this is the delayed neutron detector, and here uh, uh, these are the these are the shielding LEDs are provided. Okay, and this, whatever the neutron, delayed neutron, if it is the delayed neutron is present, those will be detected by the uh, this neutron delayed neutron detector. So this is simple, and there is a servo mechanism, is a geared motor, and this is the encoder. This is the encoder used for the particular positioning, where is to be which subassembly. Indexing, separate indexing methods are there, and top of this subsystem, here some rotating plates are there. Number is a circular disc. The indexing is inscripted there. So manually, means by visually also you can see which particular which subassembly it is located and the sample has been taken. Okay, so as I was telling, so in the at the level of the sodium capacity, detector block is provided around the this felt fuel location module housing, and silicon rubber, basically it's a dimethyl siloxane, it's a long chain. So that is used as moderator to thermalize the neutron, and the total six numbers of neutrons are neutron detectors are there in the moderator block. Okay, so this is a very simple mechanism. This is a indicative design of that particular I have shown you. But lot of if you discuss design point of view, a lot of considerations are there that I cannot uh, uh, disclose in the open forum, but this is an indicative idea through which you can understand then how the delayed neutron detection is helpful for um, identifying the failed fuel subassembly, uh, to locate the failed fuel subassembly. Okay, these encoders are whatever the optical encoders are used normally in industry, those are absolute encoder, and the protocol is synchronous serial interface, because serial communication is always preferable for long distance, because this uh, all these systems, it will be placed in the reactor containment building, but the display station and the controlling and monitoring console, it will be minimum 3 to 400 meter away, means it will travel through that signal will pass through the cable. In case of parallel communication, say the 10 bit, so 10 cables, first of all you need 10 cables, and in any one of the bit, if it is a, in case of 0 it is become 1, or in place of 1 it is become 0, then there is a huge error. What I mean to say there is a 4-bit parallel communication, so 1 0 1 0, say what, this bit is to be transmitted, this bit is transmitted um, by the sensor, then the 4 cable is going to transmit this. Due to some reason, if this 1 is become 0 at the receiving end, then the entire thing, it will be 0 0 1 0. So instead of 1 0 1 0, you are getting only 1 0, which is by decimal 2. See, there is a huge error. Okay, so to avoid this, always for sophisticated industrial application, that they will be using the SSI communication. So this QR code you can scan, and there I have explained there is a playlist will be there, 3 videos will be there, where I have clearly explained how the absolute and absolute SSI encoders can be, that uh, uh, absolute encoder output data which is uh, transmitted through SSI protocol can be read. F- we have made our own. I have designed the own our own SSI card in Modbus protocol that can be interfaced with any PLC or controller. And also I explained there in Unity Pro, means the Schneider PLC, how the particular high speed counter card is configured for interface the SSI encoders. So this was all about today's discussion. So with that we will close the uh, discussion about the delayed neutrons and its role for reactor control, as well as the application of delayed how the delayed neutron, by detecting the delayed neutron, how the failed fuel is located. Thank you so much. Thanks for your patience. We will meet with our next topic in the next discussion. Take care. Have a nice time.